quiet down, everyone. We're gonna get started on our last lecture of today. Sorry, not last lecture, but okay. So we're gonna move on. Different topic. Okay, we're gonna switch gears completely, but it's gonna be. I mean, at least I did talk about tide pools today for like 5 minutes, right? So we're gonna start talking about intertidal ecosystems. All right. I really like the intertidal ecosystem. It's my favorite ecosystem. I love going to the tide pools. We should go to the tide pool sometime, but unfortunately there's no good low tides in the summer. But yeah, we're gonna have 2 lectures on the intertidal. We're gonna have one today and one tomorrow. Today's is about the environment in general and their adaptations, right? And tomorrow we're gonna talk about something called ecology, which we'll get into later. So let's get into this one and talk about the intertidal zone, so like tide pools, right? What is the intertidal zone? It is the region near the ocean that experiences tides. That is this region only, okay? And the reason why this is the intertidal and nowhere else is intertidal is I am, yes, implying that no other region experiences tides. Up here, the terrestrial ecosystem, do they experience tides? Whether the water is going up and down, we're here in the classroom, we don't care, right? It's dry regardless of whether it's high tide or low tide. Okay, down here in the ocean where the sharks are living, do they care about the tides? Whether the water is going up and down, they are always going to be in the water anyways. They don't care. They do not experience tides. Only this part experiences tides. Half the day it is dry, half the day is wet. That's a true intertidal zone, right? So whether you're above it or below it, you do not experience the tides, and so those are not the intertidal zone. We're only talking about this part right here. More on that later. First, let's talk about how tides work, right? So does anybody know what tides are, first of all, before we begin? What is a tide? Let me just make sure it's going. What is a tide, you guys?
The water level rising.
The water level rising up and down. Yeah, exactly. Okay, sure. We'll go with that. The tides is when, the water goes up, high tide, the water goes back down, low tide. Okay, at low tide, you can go check out the tide pool. There's a lot of animals, right? At high tide, you can go surfing. It's fun. All right, so the tides goes up and down. What causes water to go up and down? That's a lot of water, right? The earth is huge. So something has to cause the water to go up and down. You said the sun, which is correct, but there's actually a more important factor. The moon, right? The moon is actually more important. Why though? The sun and moon both are exerting a force on the earth. What force? Gravity, right? Okay, the sun and moon are using the gravity force on earth and they are pulling the water towards itself. Okay, that creates what's called a tidal bulge right here. See that? That's high tide. Okay, well here's the thing. Gravity is a type of force that depends on 2 things, mass and distance. Alright? Well, the mass of the sun is way bigger than the mass of the moon, so mass alone suggests the sun has stronger gravity. However, it also is the case that distance is more important than mass, and the moon is right next to Earth and the sun is far away. So who's actually stronger? The moon, right? We feel more of the moon's gravitational pull than the sun does, so the moon governs the tides, the sun kind of just helps out, okay? All right, so the moon is pulling the water towards itself, away from the earth, creating a tidal bulge. Okay, this is not the 100% correct explanation, but it gets the point across. All right, we're just talking about distances, right? And the greater the distance, the weaker the gravity. So if you imagine 3 points, 1, 2, 3, this part being the furthest, this part being the medium, and this part being the closest, this part experiences stronger gravity than this part, okay? So right over here experiences the strongest gravity, the moon pulls the water towards itself. Right over here, the earth experiences medium gravity and the earth gets pulled towards the moon as well. And right over here, this water experiences the weakest gravity and does not get pulled as far. So the way a lot of colloquial books like to describe this is the earth is being pulled away from the water at this location. Okay? Take that with a grain of salt. That's kind of like the conventional explanation. It's not like the nitty-gritty, but it's really simple, right? The other one is way too complicated. It has to do with centripetal forces. It's going to be beyond the scope of this class. So it's okay to know this mostly correct answer, okay? The water closest to the moon gets pulled up but this water furthest away is left behind and the earth gets kind of pulled away from this water. So it ends up creating two tidal bulges, one here and one there. Okay, so each of these tidal bulges is a high tide. You guys see the water level is higher there. Consequently, where are the low tides? They are on these sides, perpendicular to the moon, the gravitational source. So it's not the case that one side is high and the other side is low. No, these are both high and the remaining sides are low. What's going on is there's a limited amount of water on Earth. The water does not change. You don't increase the amount of water on Earth and you don't decrease the water amount on Earth, right? It's always the same limited amount of water. If you want to make more water go here, it has to come from somewhere. It doesn't magically increase. It comes from here. So you take the water away from here and you put them here. Does that make sense? So in consequence, the part where you add water to becomes high tide, and the part that you take water away from becomes low tide. So you have these 4 points. Let's call them A, B, C, and D. These 4 points each represent a high and a low tide spot, right? Earth rotates once a day, okay? In 24 hours, if you are here, 24 hours later, you'll end up right here. I did the other way, it should be this way, but it doesn't matter, right? You'll end up in the same spot, and do you see how, like, since the moon doesn't really move that much around the Earth every day, it moves only like 1/27th its way around the Earth. It's not that much, so the moon just pretend it stays in the same place. But if the moon stays in the same place, then the tidal bulges stay in the same place. The tidal bulges are staying in the same place, but the Earth is rotating beneath. So depending on where you are on the Earth, you will rotate beneath each tidal bulge once in 24 hours. Does that make sense? So if you start here, 6 hours later you will be here experiencing what? Low tide. And then 6 hours later you'll be here experiencing high tide, and then low, and then high again after 24 hours. Okay, I went the wrong way again, but it really doesn't matter, right? The same concept applies. Okay, you will rotate under these tidal bulges because the tidal bulges stay relatively fixed because the moon doesn't move that much every day, whereas the Earth makes one rotation a day, right? Okay, the moon revolves around the Earth, that is true, but it takes 27 days to do so, and so each day it moves just a tiny bit. So just pretend that these tidal bulges roughly stick in the same place, okay? So what does that tell you? In 24 hours, you experience how many high tides?
2.
2 and 2 low tides. On average, right? Sometimes you'll get some overlap and you only experience 1 low tide or 1 high tide or something like that. But on average, we will experience 2 high tides and 2 low tides per day. This is the classical case. There's some strange place on Earth where you experience only 1 tide a day, but we'll talk about the general case, the one that makes the most sense, right? The ones that here on the California coast that we should be concerned with experiences 2 high tides and 2 low tides per day. Okay. Okay, so throughout the month, there might be some really high tides, really low tides, or some in-between tides. Low tides are not that low and high tides are not that high. What causes the difference in height? It is the moon position, right? The moon phase. So let's take a look at this. If the moon is either here or here, aligned with the sun and the earth, then do you see how like the sun and moon, they kind of join gravity forces and they create an extra tall tidal bulge? If they create an extra tall tidal bulge, that's an extra high tide. And they're taking more water away from the low tide as usual, so this low tide will be an extra low tide. Sounds pretty good for a tide pool excursion, right? This is known as a spring tide, right? Not spring as in the season, but spring as in the bouncing thing, because like 6 hours, every 6 hours you're like super high and then you're super low and then you're super high and super low, right? It bounces up and down really quickly. You have a really great tidal range. The difference between high tide and low tide is really great, right? That's what we call a spring tide. And spring tides are very good to go to the tide pool because you'll see a lot of things. The tide is super low. Just don't go during the spring high tide, then you will be super wet, right? notice where the moon is around the Earth. Right? This is the position of a full moon, and this is the position of a, anybody know? New moon. Yeah, I guess sometimes a solar eclipse happens, not all the time. Just because the moon is here doesn't mean a solar eclipse will happen. Right? It's a little complicated. But this is the full moon and this is the new moon. So during those two moon phases, right, there's one full moon a month and there's one new moon a month. Those are two opportunities to go to the tide pools, right? And we just had a full moon. 2 weeks later, we will have a new moon, right? Another opportunity. Okay, so there we go. Full moon or new moon, spring tide, and high tides, low tides, right? In contrast, if the moon has revolved to here or has revolved to here, and now it is at 90-degree angle, or a right angle to the sun, right? Then this kind of creates an interesting scenario. The moon is pooling water this way, right? If the moon pools water this way, where does it take the water from? From where?
Poles.
The poles like this? That's not correct. Where does it come? Remember, look, if the moon is here, it actually creates a tidal bulge here and here. So it does not pull the water away from the poles, it actually gives it to the poles. Right? But you shouldn't be really trusting this 2D diagram. So don't call it the poles, right? Just call it side, what side did I call it? D, right? Side D, okay? So A, B, C, D, right? If the moon pulls it towards side D, there's automatically a tidal bulge over here at side B. Where is it taking the water away from to do so? These two, A and C, right? But look what the sun's doing. The sun is pulling the water back to A and C, away from B and D. Do you see how the sun and moon are fighting in this case? They're kind of canceling each other out. The moon tries to pull it here, takes it away from here and here, but the sun tries to pull it here, taking it away from here and here. So they're kind of like fighting. They cancel each other out. And then you get something called a neap tide. The low tide is not that low, and the high tide is not that high. You get what's called a high low tide and a low high tide. Right? Consequently, the difference between high tide and low tide is not very significant. It's a very small tidal range because the high tide is not that high. It's kind of low. It's close to the low tide, which is not even that low. It's kind of high, so they're pretty close together. Right? It's not a really high tide or a low tide where there's a big difference. It's a low high tide and a high low tide, and the distance is really small. Okay, so that's what we get when they're aligned like this. Right? When they're aligned at right angles to each other, we get something called a neap tide scenario. And this would not be a good time to do anything. Actually, you know what? This would be a good time to go fishing because if you fish in these conditions and the tidal range is very low, then there's not that much current. Right? The current is very weak because it doesn't have to change much height. Right? But yeah, anyways, this is not like a good time to go tide pooling, right? Because the low tide is not very low. Okay, so there you go. At right angles to each other. What moon phase is this? Oh, this would be the half moon, right? You look in the sky, you see a half moon, that's a neap tide, right? This one over here is called the first quarter, and this one's called the third quarter, and they both look like the moon is just a half, right? Semicircle. Okay, so are we all okay with what causes tides? Right? The moon causes tides for the most part because of gravity, and depending on the moon's position, the high tide might be higher or lower, and the low tide might be higher or lower. Okay. All right. So let's move on and talk about the intertidal zone. So remember, this zone right here, right where the water meets the land, is the intertidal zone. The land is not intertidal, and the water is not intertidal. Regardless of how high or low the tide is, the ground here will be dry. Regardless of how high or low the water is, the ocean will still be wet. But the intertidal zone changes. If it's low tide, it will be dry. If it's high tide, it will be wet. Therefore, the intertidal zone is different from these ecosystems right over there. Okay, so keep in mind, right? If you go lower than the intertidal zone, even if you're in the ocean, it may be a little counterintuitive at first, but that part does not experience tides, okay, if you live in the ocean. Okay, so as you guys can imagine then, out of these three locations, marine, terrestrial, and intertidal, which ecosystem changes the most? Intertidal, because this one's always wet, this one's always dry, but this one, 2 times a day, dry, wet, right? So this part, always changing, right? What do we call something that's always changing? Dynamic, right? The word dynamic means always changing, okay? Never stable. So these ecosystems are always changing, and it creates for a very difficult living situation, right? You would not like to live in the intertidal zone because you're gonna have to deal with getting wet half the time. And after the high tide finishes, like, oh good, it's low tide, it can dry off. Well, guess what? 6 hours later, wet again, right? So this part is a really kind of treacherous environment. All these organisms have really, really strong adaptations, and they're very hardy, right? They're very hardy to the conditions here, and they're able to survive in the intertidal zone. So we'll get into the 2 main problems, the low tide problem and the high tide problem, and talk about how the organisms are adapted to each. Right? Starting with the high tide problem. What do you guys think the high tide problem is? Yeah, it's getting swept away, right? Waves are big during high tide. Okay, let's talk about that one first. There's a lot of water during high tide, and it crashes upon these rocks at really strong forces, right? That's actually kind of scary. I mean, like, I know most people are even afraid of standing on rocks with crashing waves, right? What do you think if you're just a tiny little limpet, right? Wouldn't you be scared if you're that small? So how do these organisms deal with the fact that these huge waves are always crashing upon their home, right? Okay, well, let's take a look. Most animals are gonna hide, right? If you can move, then you will hide. That's the rule, right? If you can move, then you will try to get away from the waves. So you can hide in between rocks in a crevice, or you can hide underneath a rock, right? So I'm talking about like a fish or a crab, right? Those guys that can move will seek shelter and hide from the waves, all right? That's cool enough if you're able to move to crawl underneath a rock. But here's the thing. What if you cannot move? Hiding under a rock does not seem like a good alternative, a good thing to do anymore, right? You're not able to move. What do? They're just gonna take the wave head on, right? If they are here right on the rock and they cannot move, then they'll just stay there, right? So let's talk about those guys, like these right here. 4 organisms that don't really move, right? Let's start off by doing a little phylum check, right? Let's make sure we still got this. What's this? What phylum is this? Echinodermata, mollusca, arthropoda. Yeah, barnacles and arthropoda. Mollusca. Yeah, good. Right, and just to remind you guys, a limpet is a gastropod. This is a bivalve, and this is an asteroidea. Right. Okay, so barnacles, mussels, limpets, and sea stars. These guys don't really move. Right. We have the top 2, which are completely sessile. We know what sessile means. They live in one place their whole life. And we have these 2 down here that are functionally sessile. They are so slow that the wave is coming and they cannot move away, right? So they are functionally sessile. They're not sessile, but they're just so slow that they might as well be sessile, right? So none of these guys can outrun the waves, and they'll just have to take it head on, right? How do they do so? Starting with the barnacle. These barnacles create cement to stick to the rocks. Right? They will secrete a cement, like a liquid cement, and then they'll stick to the rocks, so they just stuck there. The wave comes, and it cannot knock it off because the cement is really, really strong. Okay? So the barnacle cement. Going down to the limpet over here, the limpet has a really strong suctioning body part. What do you think that body part is called? It's not the siphon, it's the foot. Right? Remember, all mollusks have a foot. The foot of a gastropod is designed for suction. All right? So the limpet uses its foot for suction to hold onto the rock. Right? I didn't really mention this, but the shape of its shell is also really useful. Right? take a look at a snail. A snail kind of looks like this versus a limpet that looks like this. And the wave comes washing over. Which one do you think will get knocked off? The snail. The snail has more drag, right? By having a low profile and a conical shape, the water washes over the limpet, right? So the shape of the shell matters as well, right? Okay, but yeah, also, of course, more importantly, it's strong muscular foot suctions to the rock, right? Who else here does suction? The sea star, but not with the foot, with many tube feet, right? Yeah, so the sea star holds onto the rock with its tube feet, and over here, it's eating the mussel. Do you guys remember how it eats the mussel? Opens it, how much? Just a little bit? Yeah, then it puts its stomach, everts the stomach inside of the mussel and digests it, right? Okay, good, we still remember that. Do you remember what class the mussel is in? Class? Bivalvia, yeah. Okay, so the sea star with its 2 feet holds onto the rock, and if you've tried to pick up a sea star from the rock, it is hard. Right. Okay, so holding on by suction, and of course, lastly, we have the mussel holding onto the rock because it has these threads. Right, these are called byssal threads, and they are reputed to be as strong as like super glue and stuff like that. They can hold like cinder blocks or something. I don't know how true that is. I just know that back in the day when I used to collect mussels to feed my pet crabs, it was really hard to pull them off. So at first, we would try to twist them off the rocks, and it would work to some success. But then later we saw fishermen using screwdrivers, and it seemed to work pretty well. So you just like kind of cut the threads, right? These threads are pretty strong, and they're designed to withstand the wave action, right? So byssal threads. So if you're sessile, the key is to hold on tight, right? And just take the waves head on. Okay? It seems that waves is a bad thing, but in reality, waves are a good thing. If I were to rank, what do sea intertidal organisms hate more, high tide or low tide? The answer is low tide. They actually prefer high tide even if there's waves, right? And we'll get into why, right? High tide that brings in water will replenish the water and oxygen that was lost during low tide, right? Low tide increases the water temperature, but the high tide will make it cold again, which is good, right? Low tide will make the water saltier, but it'll make the water the normal saltiness again. And waste will collect in the small tide pools during low tide, but the high tide will wash them away. But the most important one that I want to mention to you guys is during high tide, animals can eat, right? And what I'm implying is that most tide pool animals go hungry during low tide. They cannot get up and search for food, right? During high tide is an opportunity for most intertidal organisms to eat, okay? And we'll explain why in a second. First of all, we're gonna have to talk about what's a popular feeding strategy in the intertidal zone, right? Let's look at this. Little barnacles right here, right? Let's take a look at barnacle feeding. Okay, that's what they're doing. They are opening their shells and lifting this thing out of the water to do this. What are they trying to do?
Suspension feeding.
Yeah, suspension feeding basically. Maybe we look at the structure more up close, we'll get some more information. Yeah, let's look at the next one. Here's a better one. In this video, you guys can see the thumbnail shows its foot right here, or its leg, and it's indeed segmented as it should because it's an arthropod, right? Okay, let's take a look at this one. Okay, look at that. Look at that structure right there. Kind of like a net, right? Better one, more up close. No, that's about as close as we get, I think. Oh, here we go. Let's look at this one. Okay, so it everts this, leg structure that seems to be catching these little particles. Do you see the little particles? All the little particles all over the place? It's trying to catch those little particles of plankton, so it's doing filter feeding, right? Here's a question for you guys. Can you filter feed in the air? No, you have to have water to filter feed. So consequently, do we see the difference between high tide and low tide now? If you're a filter feeder, you cannot eat during low tide, yet you can eat during high tide. So even if the waves are annoying and strong and huge, they are actually providing food for the organisms, right? Especially if you're a filter feeder like a mussel or barnacle, right? The waves are really important. They bring in food. Okay, let's look at these animals right over here. Turban snail, the gastropod, here's a limpet, right? Here's its foot, those are its eye stalks, and this is its radula, right? What do you do with the radula again? How though? You scrape the algae off of the rock, right? And sea urchins, we all remember how sea urchins eat, right? All three of these, what is their feeding style? What is their feeding style? Oh, I wrote it there. Grazing, right? So, we have grazers, right? These guys walk around during high tide and they graze. When we talk about low tide, we will talk about why these guys cannot do their grazing during low tide, okay? It's not like they depend on the water like a filter feeder does, like you're not even able to filter feed on land. They can graze during the low tide, but it's a bad idea to graze during the low tide. We'll talk about why in a second. Okay, so these guys are grazing during high tide. High tide is an opportunity for them to be eating as well. Okay? All right, so during low tide, like I just mentioned, they cannot eat. Why can't they not eat? Why can't they do their grazing? Because they are too busy concentrating on a different task, conserving water. All right, water conservation during low tide is the biggest problem. Right, they really have to watch out for losing water. So let's get into the low tide problems. The main problem during low tide is called desiccation. And this time I'm actually going to check the spelling. So to give you guys a clue, there are two C's, not S's. Okay? Desiccation means drying out. So if you guys heard of like a desiccant, right? If you don't know what a desiccant is, I bet you have encountered one, right? Maybe in those like dry Asian food packets, right? You might see a little thing that says "do not eat," right? The little bag. That little bag is a chemical that absorbs water, right? It's called a desiccant. It absorbs water, and when something absorbs water, it is absorbing the water away from something else. The thing that the water is being water absorbed away from is actually getting drier. Does that make sense? So desiccation refers to drying out, and a desiccant is a chemical that dries something out. All right? So the organisms here have to worry about desiccation with two C's, right? This is a bigger problem than the waves, all right, as we'll see. Do sea animals like being dry? No, right? We'll see why in a second. But here's some other, low tide problems, right? At low tide, there's less water than during normal. So because there's less water and there's only the small shallow pools, the small shallow pools get warmer faster, right? And they don't like warm water. They want to be cold like the normal ocean is, right? Also, there's less oxygen in warmer water, right? The salinity might go up because the water is evaporating, leaving the salt behind. And of course, sea creatures don't like to dry out, right? This is a big thing. Sea creatures are afraid of desiccation. Let's see how, cartoons handle desiccation and see whether sea animals really like being on land or not. Let's take a look at this clip. Yeah, so what's going on here, right? We have SpongeBob and Patrick finding themselves inside of an underwater terrarium, right? Oh man, you couldn't hear that. I gotta make that louder. All right. There we go.
Patrick, air is not good. You're just being shy. Don't worry, buddy. You're doing fine. I won't let you blow this.
guys remember what happens when Sandy finds them later? Yeah, you see a real dry sponge and a real sea star that look like this, remember? So I thought that was pretty creative. What are they facing? They're facing desiccation, right? They're being dried out. And sea animals don't like to be dried out. That defeats the purpose of being a sea animal, right? So these guys have special adaptations, right? This is just a quick definition, adaptation. Pretty sure we know what that means, but you need really, really strong adaptations to be able to survive desiccation, and almost no sea animals have this, right? Most sea animals do not worry about desiccation. They live in the ocean. The ocean is wet. Why do they have to worry about it, right? But the ones in the intertidal zone, do they have to worry about desiccation? Yes, because it happens twice a day, low tide, right? So how do you fight desiccation? Let's talk about these guys, limpets again. In order to conserve water, they suck down tightly to the rock, and hopefully they can hold some water in between the rock and their shell, right? So underneath, right, here's their body. Their body's this, and hopefully on the corners, they're holding some water in, mainly to keep their gills moist, right? They need to keep their gills moist if they want to keep breathing. Okay, and if they ever need some oxygen, they may be able to lift their shells just a tiny bit to get some air to go inside, but not too much, because if there's too much, if they lift their shells too much, what will happen? Their water will just leak out and they will dry out. So, do you think it's a good idea for the limpet to go eating and grazing during low tide? No. You see what I'm saying now? They cannot eat during low tide because that implies that the limpet's gonna have to crawl around, lift up its shell and crawl around and sacrifice its water supply. It's not gonna do that. It's gonna go hungry, and essentially it's going to fast for 6 hours until the water comes back. And then it's safe to walk around again. That makes sense? Right, so these guys, they're just waiting out the low tide, holding onto the rocks to conserve their water supply. They do get really hungry though, right? So imagine if we had, let me use green for this, right? So if we had a rock, and the rock is covered in algae like this, okay? And then here's a limpet, it crawls over here, there's a limpet, and now it's low tide. Limpet can no longer move because it doesn't want to lose its water supply. So what does it do? It eats all the algae underneath its shell. So when the limpet leaves, it leaves an empty circle on the rock there. Just a circular patch that has no more algae, right? That's kind of funny sometimes. You know, the limpet has camped out there for 6 hours during low tide and got hungry and was eating the algae underneath its shell. Right? Okay. So that's for limpets, right? What about other ones like snails? Snails, they don't hold on to the rocks. Instead, they have a nice little door, right? The door is also called an operculum, which is the same word that is used to describe the osteichthyes gill cover, right? So you can call it a door, you can call it operculum, either one is fine. Right? But snails, they have this door, and when they shut the door, they can hold the water inside their shell. That is the advantage of being a mollusk. If you have a shell, you can hold water inside your shell. Okay? At the same time, snails actually have a little behavioral adaptation. So check this out. Look at these snails. We got periwinkles on the left, turban snails up here. These guys are all huddling together, right? They know what they're doing. They all congregate together to await the low tide and to last it out together, right? By being in a big group like this, it dries out slower, all right? Forming these congregations dries out slower. But not only that, look where they are congregating. On top of the rock or in between the crevice. You guys see that? They know where most of the water is. The water is mostly inside the crevices. The crevices dry out slower than the surface of the rock does. The surface of the rock dries out the fastest. So they're all huddling in the crevices where there's the most water, and by huddling, they also reduce the evaporation from their bodies. Okay? So they all have this little behavioral adaptation in order to conserve water as well. Okay, so another adaptation against desiccation. Okay, continue on to other animals. These ones with two shells, barnacles and bivalves like the mussel, they just close their shells tight and they hold water inside the shell. Again, an adaptation for holding water is to have a nice shell. What are these shells made out of?
Calcium carbonate.
Calcium carbonate, good, yeah. The mussel and the barnacle shell are both calcareous and they're good at holding in water. This one has two halves to it, but keep in mind this is not a bivalve, it's not a mollusk, it's actually an arthropod related to a crab, right? It just has a weird life, right? Okay, so these guys, they close their shells. What does the mussel use to close its shell tightly? The adductor muscle, right? Let's make sure we remember those body parts. And there you go. It can hold water inside its shell, and is very, very effective at doing so. I remember one time I harvested some mussels, and I put the live ones inside my fridge, and after a week, they were still alive. So they were able to use that water in their shell for at least a week. Who knows, maybe even longer, right? So these guys, keep in mind, they're only required to hold the water in their shell for 6 hours, but they can do for several days. I guess it's just a little insurance kind of thing, right? If they don't get a couple days worth of water, then they can survive. And then when the water comes back, they're good. Right? Okay, so closing your shells, right? Continuing on, sea anemones, a cnidarian here does not have a shell, so it cannot hold the water inside of a shell. So instead it does something else, another behavioral adaptation. These guys withdraw their tentacles into their body, right? By withdrawing their tentacles, they reduce their surface area. Because look at this, each one of these tentacles has surface area and water can evaporate from that. But by withdrawing their tentacles, they become like this donut shape and there's less surface area and they dry out slower. Okay, so withdrawing tentacles. Take a look at this picture real quick. We have sea stars, but more importantly, we have sea anemones, some up here and some down here. Look at these guys. Those guys are greedy, right? During low tide, they still have water and they're able to be open like that, right? This is the importance of larval settlement, right? Who chose the better spot? These guys right here, right? You can imagine when the sea anemones were all little planula larvae, right? Planula, you guys remember that? They were all hoping to find a spot on this rock. They were all trying to get these spots down here, but when these lucky ones got there first, a few of them were forced up here into the worst areas, right? So that's the importance of larval settlement. They really need to choose a good spot because they have to stay there their whole lives. And look at these guys. These guys got it easy. During low tide, and they don't even have to do anything. They still got the water, right? But these guys, they actually have to use their adaptations and withdraw their tentacles and go hungry. These guys are actually still eating during low tide, right? Okay, so that's sea anemones, right? So these guys that we just talked about were all pretty much sessile, right? Or functionally sessile. The limpets, the snails, the barnacles, the mussels, and now we have sea anemones, right? Sessile organisms. But we have not mentioned the motile ones. What do motile ones do during high tide again? They hide, right? So what do they do during low tide? Well, guess what? They can walk around, right? The crab has a shell that is separate from their legs. What does that mean? That means that they can hold water in their shell and move. Remember the limpet? The limpet can hold water in a shell, but it can't move, right? Because if it moves, the water will come out. The crab has water in its shell, but its legs are separate from it, so it can still move around during low tide, right? So it can move around and carry the water with it. So as a consequence to that, what is the crab able to do during low tide that the other ones cannot? What can they do? They can eat, right? They can move around and actually eat. Okay, so that's a really cool thing. The crabs, although they are not strongly attached to the rock, and withstanding the waves, these guys will get knocked off probably. They can at least walk around during low tide and eat, right? So that's a good thing. Okay, so the crab, right? They can walk around during low tide and eat, and being able to move is good because during low tide is a good opportunity for a seagull to come in and start picking up limpets and stuff to eat. The limpet's not going to move away, so it's doomed, right? But the crab, if the seagull comes in trying to get the crab can run away, right? That's one good advantage of being motile during low tide. Okay, so the crab can move around and eat during low tide. Let's look at a crab eating in this video clip real quick. And maybe you guys can tell me its feeding style. Alright, so here's a striped shore crab. And it is eating during low tide. Right? You see it's completely dry right now. It could be, yeah. But if the thing that's eating is alive, it's probably an algae. Grazing. Right? But it could be scavenging if it is trying to pick out something dead. But usually they go after anything that's stuck to the rocks. So algae or barnacles or periwinkles, all of those would be considered grazing. I want to show you something cool. I don't know if you guys noticed, but the crab kind of ducks down a little bit to allow the water to move over it. It also helps to have a flat carapace, not a bumpy one. Right? But now it's standing up again, like the wave has passed. Okay, so we'll just watch to there, and that's it. Okay, so this is our first intro to the intertidal zone. We know how the tides work now, and we know why it's called the intertidal zone. Next time when we get into this, we'll get into the details, right? We'll talk about the different zones, right? The high zones and the lower zones, who lives in each of them, and how the organisms interact with each other to assemble into each of those zones. Okay? So, any questions about this? Everybody good? Okay, cool. So just another reminder, got a quiz on Thursday. It does not cover intertidal, but it does cover deep sea. So be ready for that. There will be a worksheet out, posted today. Wait, did you guys get the deep sea worksheet already? No, right? Okay, yeah, so there'll be a worksheet posted, and it's going to be due tonight. Okay, so you guys should try to finish that.
Is it the 9.5 one?
No, 10.
Okay, so we have two.
Yeah, so there's gonna be another one due today. Yeah, so then that way you guys can get the solutions tomorrow. And then food trip on Saturday. Epipelagic, plankton,